In this video, we will be talking about derivatives and integrals of vector functions. But before we get into that, let's do some quick review from Calculus 1. Consider the function f of x equals 1/4 x squared plus 1 graphed below on the closed interval from 0 to 4. F of x contains the points p located at 2, 2 and q located at 4, 5. So the idea in Calculus 1 is we start off with connecting 2 points on a curve, P and Q. And if I connect these with a line, this is called the secant line. And the way that we find the slope of the secant line is by taking the y-coordinates, subtracting them, and then dividing that by the difference in the x-coordinates. The whole reason that we care about the slope of the secant line is because it tells us about the average rate of change for our function. And where we would like to get to is we would like to create the tangent line at a given point. So oftentimes what we'll do is we'll make P the fixed point and Q a changing point or a dynamic point. And so we would like to find the tangent line at P because the tangent line tells us about something that is called the instantaneous rate of change. So how do we get the slope of the tangent line? Well, here's a little review of what we would do in Calculus 1. Like I said before, I'm going to keep my p-value or my p-point fixed, and I'm going to choose some arbitrary point on my graph as well. And in this case, even though we know the ordered pair for p, I'm going to generalize this and say, let's say this x value is x, and I want the distance between my 2 points to be h. So I want the distance from here to here to be h units, meaning that I'm going to have this x value be x plus h. So that now what I'm doing is I'm taking the slope of this secant line, and notice that this is a closer point to P. And so here, this y value, that would be f of x, and this y value here would be f of x plus h. So for this particular secant line, if we wanted to find the slope of it, we'd have the slope of the secant line is equal to the y value f of x plus h minus the other y value f of x, and then over the difference in the x values, so x plus h minus x, and notice that that just simplifies to h. And recall that this thing is called the difference quotient. Now, as a reminder, our goal is to get the slope of the tangent line, which is this green line here, and the way that we can approximate it is by taking smaller and smaller values of h. And again, in Calculus 1, we learn about h going to 0, and we learn about this thing called a limit. So then we learn that the slope of our tangent line, or in other words, the instantaneous rate of change, is equal to f prime of x, our derivative function, which is equal to the limit as h approaches 0 of our difference quotient, f of x plus h minus f of x all over h. All right, so I've taken the steps to start taking the limit definition of our derivative for this particular function that we are looking at, f of x. And I'm at the stage where now I have the limit as h approaches 0. Notice that the remaining two terms both have an h in it. I can factor those out and divide that with the h in the denominator, giving me the limit as h approaches 0 of 1/2 x plus 1/4 h. And Now I no longer have an h in the denominator, meaning that I can use direct substitution. And if I plug in h equals 0, notice that for all this work, we get that the derivative is the function 1/2 x. Now, the really nice thing that we learn about in Calculus 1 is we learn about these rules to take derivatives so that we don't have to go through this long process of evaluating a limit or the limit definition of a derivative. And for this function in particular, if I wanted to take its derivative f prime of x, I can use the power rule. If I bring the power down, that ends up giving me 1/2 because 2 times 1/4 is 1/2. And then we have x, and I decrease the power by 1, so we can get our derivative function that way. So again, I just want to reiterate, we found our derivative function f prime of x to equal 1/2 x. The reason that we care about this function is now anywhere along my original function, I can find the slope of the tangent line or the instantaneous rate of change. So let's find it where we were originally looking. So suppose this is our tangent line right here, and we'd like to find the slope of that tangent line. Because I know in this particular example, the the point P has an x value of 2, that means that I can evaluate my derivative at x equals 2, and if I simplify this, that gives me 1. So by doing that, we found the slope of the tangent line, which is also the instantaneous rate of change. And then finally, another thing that we can do is we can find the equation of the tangent line. I've provided that here in point-slope form, as well as slope-intercept form. So that is a quick overview of limits and derivatives from Calculus 1. Now let's talk about derivatives and integrals of vector functions. The derivative r prime of t of a vector-valued function r of t is defined in much the same way as it was for real-valued functions. That is, the derivative with respect to t, or r prime of t, is equal to the limit as h approaches 0 of r of t plus h minus r of t over h. So now we're in 3 dimensions, and we're looking at this space curve that I am calling C here. So there's our curve, and we're once again looking at a point P and a point Q on our space curve. Now, the difference is that in order to get to P, we describe it with this vector r of t, and then in order to get to Q, we're calling that some other vector r of t plus h. And then you can almost think of this as a secant vector. We get this by subtracting those two position vectors. So the geometric significance of this definition is shown in the diagrams to the right. If the points P and Q have position vectors r of t and r of t plus h, then the vector PQ represents the vector r of t plus h minus r of t, which can therefore be regarded as a secant vector. If h is positive, the scalar multiple r of t plus h minus r of t all over h has the same direction, and as h approaches 0, it appears that this vector approaches a vector that lies on the tangent line. For this reason, the vector r prime of t is called the tangent vector to the curve, provided it exists and is non-zero. This is shown to the right. So here is what we are referring to. This vector here we can call the tangent vector. We will also have occasion to consider the unit tangent vector, which is given by capital T, which is equal to the tangent vector divided by the magnitude of the tangent vector, which is how we calculate a unit vector in general. The following theorem gives us a convenient method for computing the derivative of a vector function r of t. We just differentiate each component of r of t. So here's the theorem that I was just referencing. If r of t has the components that are differentiable functions f, g, and h, then r prime of t is equal to f prime of t, comma g prime of t, comma h prime of t. Example 1 says find the velocity, speed, and acceleration of a particle whose motion in space is given by the position vector r of t. All right, so let's start with the velocity. The velocity vector function is equal to r prime of t, so I'm going to, based off this theorem, take the derivatives of each of the components individually. First we have 2 cosine of t. Its derivative would be negative 2 sine of t. Then the next derivative would be 2 cosine of t. And for the last component, I'm going to need to use chain rule. So I'm going to bring the power down. That gives us 10 cosine of t. And then I need to multiply by the derivative of the inner function cosine. So that would be negative sine of t. And I'm just going to rewrite that. All right, so now let's move on to the speed, which is the magnitude of the velocity vector function. And remember, for a vector, the way that we find the magnitude is by squaring each of the components and then adding them together and then taking the square root of that. So I have the square root. I'm going to square each of the components and then add them together underneath the square root. That gives me 4 sine squared t plus 4 cosine squared t plus 100 sine squared t cosine squared t. And we can do some simplification here, because if you factor out a 4 from the first two terms, you get the Pythagorean identity. So this is equal to 4 times sine squared t plus cosine squared t plus 100 sine squared t cosine squared t. Because this is the Pythagorean identity, that whole thing is equal to 1. All right, so we could just leave the answer like this. In terms of further simplification, if you wanted to, notice that both terms are divisible by 4, and then we could take the square root of 4, which is 2, and bring that outside the square root. I'm okay either way. One thing I do really want to emphasize is, because sometimes my students are on the struggle bus in terms of their algebra, this is not equal to either without the square root or with the square root. This is not the same thing as 2 plus 10 sine of t cosine of t. Those are not the same thing. So please be wary of that. Here, this would represent our final answer for the speed. All right, now for the acceleration, I would take the derivative of our velocity vector function. And before I do that, I just want to point out, I'm going to rewrite the z component because I don't want to use the product rule when I'm taking the derivative of that thing. If you use a trig identity, you might see that this is related to the double angle identity for sine. And so this is the same thing as negative 5 times sine of 2t. And now if I take the derivative of that, I no longer have to use the product rule. So let's go ahead and take the derivative of each of these components. This is going to be negative 2 cosine of t. And then, so that was the derivative of that. Now we want to take the derivative of 2 times cosine of t. That's negative 2 times sine of t. And then the last derivative, we have negative 5 times cosine of 2t, and then I need to use the chain rule. So I'm going to multiply that by 2, and that would be negative 10. So there is our acceleration vector function. Example 2 says find the unit tangent vector of the curve r of t given. And if you don't remember from the previous page, the unit tangent vector is equal to r prime of t divided by the magnitude of r prime of t. And please make sure that you have this memorized. This is an important formula. So if we're going to do that, then off to the side here, I'm going to find r prime of t first. Okay, so I found that. Let's find the magnitude of r prime of t. I'm going to square each component. Okay, and notice again that if we factor out a 9 from the first two terms, we get the Pythagorean identity. So that's going to give us 9 plus 4t squared underneath the square root. So let's put this all together. All right, so I've gone ahead and I've written it where I have the derivative vector in the numerator and then the magnitude in the denominator. There's several other different ways that you could write this. Notice that I could write this as 1 over the square root of 9 plus 4t squared, and then just copy my vector. If I wanted to, I could also distribute this into each of the three components, but I'm not going to do that, and I'm just going to leave it factored out like this, and here we have our final answer. Here's a theorem. Suppose u and v are differentiable vector functions, c is a scalar, and f is a real valued function. Then the following 6 properties hold true. They're pretty similar to properties of derivatives of real valued functions. Like, for example, we have the constant multiple rule. If I take the derivative of a constant times a vector valued function, I can pull the constant out and then take the derivative. This would be analogous to the product rule, and this is analogous to the chain rule. So stuff we've mostly seen before. Let's talk about integrals. The integral from a to b of r of t dt works very similarly to derivatives. We take the integral of each of the component vector functions, the component functions. Example 3 says, suppose r of t is equal to that, evaluate the following integrals. All right, so if we're taking the indefinite integral to start off with, we end up with the integral of cosine of t dt, the integral of 1 dt, notice that's the coefficient of j, and then the integral of negative, let's factor out the negative, so negative 2t dt. All right, from here, notice that these are indefinite integrals, and so I have sine of t, and then don't forget our constant of integration, and this is a scalar, so maybe I'll just put c1. Then we have t plus a different scalar, c2, and then minus t squared plus c3. And another way that we could go about writing this is I can pull out all of the constants and write this as a sum of two vectors. So I've written that as the sum of two vectors, but more commonly, instead of writing it like that, I'm just going to put some vector constant like that. And so this would be our final answer. All right, so in part B, we're taking the definite integral, and since we already did the indefinite integral in part A, I've just copied down that vector, and this works very similarly to the integration of real valued functions. Now I'm just going to plug in pi and 0, just like we would with a normal integral. Now our answer is just going to be a vector as a final answer. So if we evaluate these sign values and subtract, we should get as a final answer 0, pi, negative pi squared. So there is our final answer for part B. Example 4 says, suppose we don't know the path of a hang glider, but only its acceleration vector, a of t. We also know that at takeoff, where t equals 0, the glider departed from the point 3, 5, 0, with velocity v of 0 equals 4j. Find the glider's position as a function of t. Okay, so here's a quick game plan. We're given the acceleration vector function. From there, we can find the velocity function by taking the integral of the acceleration, and then from there we can find the position vector function from integrating our velocity function. So let's go ahead and start. Okay, so we're taking an indefinite integral here. I'm going to integrate each component, and if we do that, that gives us negative 3 sine t, 3 cosine t, and 2t. Because this is an indefinite integral, I need to add my constant vector. And just like in Calculus 2, in order to figure out our constant, we're going to need to utilize some information that we're given, maybe an initial condition. So here we know that v of 0 is equal to 4j, so let's utilize that. All right, so I know that v of 0 is equal to 4 times vector j, and we have the velocity function, so I'm going to go ahead and plug in 0 for t. Okay, so sine of 0 is 0, cosine of 0 is 1, times 3 is 3, 0, and instead of 4j, I'm going to rewrite that. That is the same thing as 0, 4, 0. And if I subtract 0, 3, 0 from both sides of this equation, we get that the c vector is equal to 0, 1, 0. So coming back up here, to each component, I'm going to add the components of our c vector. So to the first component, I'm adding 0, which means that it stays the same. To my second component, I'm adding 1, so I have cosine of t plus 1 like that. And then to the last component, I'm adding 0, so that also remains the same. So here, again, this is our velocity function. All right, so now we are at item number 2 in our game plan. We want to find the position function by integrating our velocity function. So I'm going to go ahead and integrate each component here, and doing so will give us 3 cosine of t, 3 sine of t, and then I need to integrate the 1, so that's plus t, and then t squared. And again, we need to add a constant vector. We've already used c, so I'm going to call this other one vector d, which is, again, it's just a constant vector, but I wanted to name it something different. Let's see. Something that we want to note is the glider departed from the point 3, 5, 0. That is another initial condition that tells us that r of 0 is equal to 3, 5, 0. So let's go ahead and plug in 0. All right, 3 times cosine of 0, that is 3. and then the other two components are going to be 0. Okay, so if I subtract both sides by this vector, that will give us that vector d is equal to 3, 5, 0 minus 3, 0, 0, which is equal to 0, 5, 0. Okay, so finally we can take our constant that we just found, plug that into that vector, and then we get that our position vector function r of t is equal to 3 cosine of t, 3 sine of t, plus t plus 5, comma t squared. And this is our position vector function. That concludes this video. Thanks for watching.